Welcome to my class. In our last few classes on network theory, we have already learned about various passive elements, their various connections like star, delta, series, parallel, and how to simplify those networks. And we have also learned about various energy sources like voltage source, current source. Now in electrical network, practically there may be scenarios like suppose if we have voltage source in any part of that electrical network, and if we see that instead of voltage source, if there is a current source, then it becomes easier for us to simplify that part, and vice versa. If we have current source and in place of that, suppose if we have voltage, then it becomes easier for us to simplify that electrical network. Now in those cases we have different techniques in circuit theory that if we apply, then a voltage source can be transformed into an equivalent current source, or a current source can be transformed into an equivalent voltage source. In today's class we will be learning about those theories, and we will also simplify a few numericals based on those concepts. So let's start the class.
So first we will see that how we can transform a voltage source into an equivalent current source. Voltage to current source transformation rule says that if we have a practical voltage source consists of an ideal voltage source in series with a internal impedance that can be converted to a practical current source with an impedance in parallel having the same value. So if we have a voltage source, and with that if we have a resistance or impedance in series, then that can be converted or transformed into a current source with the same resistance in parallel this time. So with the voltage source, the resistance or impedance will be in series, and with the current source, the resistance or impedance will be in parallel in the transform circuit. Now let's understand that with a circuit. Suppose between these two terminals AB, we have a voltage source having value V and a resistance having value R. Now if we connect these two terminals, if we short them or if we connect them by wire, then it will be a closed loop or mesh or path. So current will flow. So the current supplied by the voltage source, if the value is I, then it will, since this is a purely resistive circuit, so it will obey Ohm's law, and from that law we know that it will be V is equal to I into R. So the current that flows through this circuit, that value will be V by R. Now what we can do is between two terminals, this voltage source and the resistance which is connected in series, they can be converted into a current source, and this resistance having the same value, it will be connected this time in parallel. So it will look like this. So the current value of this current source will be I, which is V by divided by R, and this resistance which this time is connected in parallel, it will have the same value, and they will be connected between the same terminals A and B. Now we will see next that how a current source can be converted to a voltage source. In case of in an electrical network, if we have a practical current source, means we have an ideal current source, and in parallel we have an internal resistance or impedance. So this time it will be connected in parallel. They can be transformed or converted to a practical voltage source, and this time with that voltage source, the resistance or impedance will be connected in series. So it says that in an electrical network, if we have a current source, and with that current source, if we have a resistance or impedance connected in parallel, then that part of the circuit can be transformed or converted into a voltage source, and with that voltage source, the same resistance or impedance will be this time connected in series, and they will be connected between the same terminal. So let's understand that with a circuit diagram. Now suppose we have a current source and a parallelly connected resistance between these two terminals, suppose A and B. Suppose the current value of that current source is I, and the resistance value of that resistor is R. So what will be the voltage drop between these two terminals AB? Again, it will obey Ohm's law. So it will be V is equal to I into R. So that means the voltage drop across this resistor or voltage value across these two terminals AB will be V, and that is I multiplied by R. So between these two terminals, now if we replace this current source by a voltage source, it will look like this. So this will be the voltage source having value V, where V is equal to I multiplied by R, and this resistor will have the same resistance value R, and they will be connected between this two terminals, the same terminals A and V. So this is how a current source can be converted to a voltage source, provided with that current source the resistance should be connected in parallel, and in the converted or transform circuit the resistance having the same value will be connected in series. But if we see in network, in an electrical network, that the resistance is connected in parallel with that voltage source, or the resistance is connected in series with that current source, so that there we cannot apply this transformation rule. Now we will simplify a few more problems and we'll understand in a better way. Now here in this electrical network, what we need to find out is we have to find out the current value flowing through the load resistor, which has the value 3 ohm. That means this resistor, by applying the source transformation rule. Now in the whole circuit, if we analyze this, then we can see that we have a current source. But here with this current source, we don't have any resistor which is directly, definitely we have this resistor. These two resistances are connected in series, and then that equivalent resistor is connected in parallel with this current source. But we will not apply the current source transformation rule here, because since this is the concerned resistor through which the current value we need to find out, so we will not touch here. I mean, we will not change anything here, and we will analyze the circuit. We will see that if we have any more energy source or not. Yes, we have. If we come to this side of the network, we find that there is a voltage source, and with this voltage source we have this resistor having the resistance value 6 ohm, and they are connected in series. So we can apply the source transformation rule here. Now this is the voltage value is 24 volt, and the resistance value is 6 ohm. So the current value will be, by applying Ohm's law, it will be V upon R. That means in the transform circuit, we will have a current source having value 4 ampere, and the resistor having 6 ohm resistance value, that will be connected in parallel. So this will, the transform circuit will look like this. This is the current source having value 4 ampere this time, and with that the 6 ohm resistor, this resistor is connected in parallel, and already between these two terminals A B we had a resistor which had the 6 ohm value that was connected. So that will remain in the circuit between these two terminals A B, and this time will be, the current source will be connected in parallel between these two terminals A B, which is connected that way, and also the resistor will be connected in parallel between these two terminals, which is connected between A B. So this time in the transform circuit, this tree will be connected in parallel, and rest of the part of the circuit will remain same. Now as we have to simplify further, as we can see here, this 6 ohm, this and this 6 ohm, these two resistors having these two resistors are connected in parallel, so we have to find out the equivalent resistance of them. So equivalent resistance, simply we know the rule, so it will be multiplication of those two values upon summation of those two values. So, and as we know, if suppose two resistances or two resistors are connected in parallel, and if they have the same value, so in the equivalent resistance will have the half of their value. So without applying this formula directly, we can write. Now in the transform circuit, now the transform circuit will look like this. So will have this current source having 4 ampere current value, and this 3 ohm is nothing but the equivalent resistance of these two resistors, and we already had this was A and this was B, and rest of the part still will remain same. This is 1 ohm, the current source, and this is the load resistor, and this is 1 ohm that we already had in the original circuit. Now what more we can do? Now we can see here that we have this current source in this circuit, and with that current source this 3 ohm resistor is connected in parallel. So here what we can do is we can transform this current source into a voltage source, and again they will obey Ohm's law. So it will be again, the voltage value will be I multiplied by R. So this time the current value is 4 ampere and the resistance value is 3. So it will be 12 volt. Now in the transform circuit, we will have this voltage source 12 volt, and between these two terminals we will have this 12 volt voltage source, and this 3 ohm will be this time connected in series with that voltage value or with that voltage source. So accordingly it is connected 12 volt, and this 3 ohm resistor now is connected between, suppose this is A and this is B. So between these two terminals they are connected. Now all and the rest of the path of the circuit is same as before. Now in this circuit we can see that this 3 ohm and this 1 ohm, they are connected in series. So the equivalent resistance will be 4 ohm. That 4 ohm equivalent resistance of these two resistances will be 4 ohm, and that 4 ohm resistor will be connected in series with this voltage source. So that part of the circuit where we have a voltage source having value 12 volt and that resistance having value 4 ohm again can be transformed into a current source. So the current value of that current source will be again 12 volt divided by 4 ohms, so it will be 3 ampere, and that's what has been drawn here in this circuit. 3 ampere between these two terminals. So these two terminals means again A and B. So between these two terminals this 12 volt will be converted into a current source having value 3 ampere, and that's what has been drawn here. And with that in this circuit we have this 3 ohm connected in series, and in the transform circuit that 3 plus 1 we have equivalent resistance having value 4 ohm, and that 4 ohm was connected in series with this voltage source. This time that 4 ohm will be connected in parallel with this current source. Now in this circuit what we can see is between this AB terminals we have a current source, we have this resistance, again between this terminal, this and this terminal they are same, and this terminal and this terminal they are same. So we can say that between AB terminals again this current source is connected, and again we can say between these two terminals these two resistances are connected, though they are connected in series with each other, but altogether, these two are connected in series between these two terminals. Since both the current sources are connected between the same terminals AB, so we can take their net value. So here we can see that this current source is supplying the current in upward direction, and that value is 3 ampere, and that is coming towards this point A, and this current source is supplying current in downward direction value 2 ampere, and that is coming from, as if we can say that it is coming from A. So the net value of these two current sources will be 3 ampere in upward direction and 2 ampere in downward direction. So net current will be 3 minus 2, so it will be 1 ampere, and that will be in upward direction. Now in the final circuit between these two terminals AB, what we have is we have a current source which has the net value of 3 ampere and 2 ampere. So it is 1 ampere since they were flowing, delivering current in opposite direction with each other. And between these two terminals we have this resistance having value 4 ohm, and we had these two resistances which are connected in series with each other. But if we see the equivalent resistance of these two resistances, then they are connected between these two terminals means AB. So we can, what we find is in the final circuit is between these two terminals we have a current source and we have two parallel paths. So here we can apply the current division rule, And since we here we are focused to find out the current value through this load resistor, which has the value 3 ohm, that means the current value that we will be finding out for this 3 ohm. So as per the current division rule, the current value through this 3 ohm resistor will be the opposite resistance, which is 4 ohm, this value, divided by the sum of the resistances 4 plus 1 plus 3 multiplied by the main current, which is 1 ampere. So it will be 4 divided by, and also since here the resistance value is 4 ohm, and also the net resistance of this two resistances which are connected in series, that is also 4 ohm. That means in the parallel path both the resistances are having the same value. So the main current 1 ampere this time will be divided into two equal halves. The same current will be flowing through each of these parallel paths. Now in the previous problem, we had a DC network where we had multiple resistances. Now, in this problem or in this circuit, what we can see is we have we have three resistances having their own value, and with this resistance, we have a inductor. They are connected in series, and we have the two voltage sources, and also these voltage sources are AC voltage source. Now, for the resistances, their values are expressed in ohm, and in case of inductor, the inductance value is not represented in terms of Henry, rather it is written 4J ohm. XL will be omega L, where omega is the angular frequency of the supply. So, if we represent in terms of linear frequency, then it will be 2 pi f into L. So if we put the value of the supply frequency, whatever it is, and if we put the value of this inductance of that inductor, then we will be getting the value of this inductive reactance. And the unit of that inductive reactance is ohm. So this value is not of an inductance, this value is of an inductive reactance. And reactance is equivalent to resistance, and if we combine resistance and reactance, we get the impedance value of that path. So we know that in case of AC circuit, we have two types of representation: polar and Cartesian or rectangular. In case of polar, the format is R, and we represent then also by an angle which is theta. In case of rectangular, the format is x plus iy or x plus jy, whatever way we want to represent. So here what we can say is the values of these voltage sources, they are given in polar form, and since resistance is a DC component, so if it is suppose for this resistance, if it is suppose given 4 ohm, then it can be represented in polar format this way: 4 and then angle is 0 degree, and this 4 ohm if we want to represent in rectangular or Cartesian format, then we can say that we can represent that 4 plus j into 0. So in both the formats we can represent a resistance value, and in case of inductor, the value of the inductive reactance which is given, it is 4j. So we can say this value is given or represented in rectangular format. Now we know that if we want to add or subtract two values in case of AC circuit, what we do is we do that in form of rectangular. So if two values are represented in a rectangular format, then we can directly apply addition or subtraction of those two values. And if we want to apply multiplication or division, then we what if these two values are given in polar format, then it is easier for us to apply it will be easier for us to multiply or divide those two values. Now when we are applying addition or subtraction, and if we see that those values are not given, or maybe one of them is not given in rectangular format, then what we have to do is we have to first convert that polar format into rectangular format, and then we have to apply the rule of addition or subtraction. And in on the other hand, when we want to apply multiplication or division, and if we see that those two values or maybe one of them is not given in polar format, then what we have to do is we have to first convert that rectangular format into an equivalent polar format, and then we have to apply multiplication or division, whatever we want to. So here we are focusing on the source transformation rule, and then we want to find out finally the current value which is flowing through this inductor. That means the current value which is flowing through this path or through this branch, where we have our resistance 3 ohm and inductor whose inductive reactance value is 4J. Now what we can do is we have voltage sources on either side, and with that voltage source we have a resistance which is connected in series. So what we can do is we can convert voltage source into current source, and then we can simplify further. So now if we apply this source transformation rule on this side, then again it will obey Ohm's law. That means V is equal to IR. So from this side, from left side, the current value, it will be V by R. So it will be 20 angle 30 degree divided by 4 ohm. So it will be 5 and then 30 degree. And from the right side, if we apply the source transformation rule, and if we apply Ohm's law, then it will be, the current value will be 10, then angle 45, it is given in polar form, and then divided by 6. It will be directly 20 by 4, since 4 is a value of a resistance, so it doesn't matter whether it is given in polar or rectangular, because if we want to represent in polar format, it will be 4 and then 0 degree. So 20 by 4, it will be 5, and 30, and this angle will be, suppose if it is 0 degree, then 30 minus 0, it will be 30 degree. Since the angles are subtracted in case of division, so it will, again it can be thought this way, 6 and 0 degree. So 10 by 6, it will be 1.67, and 45 degree minus 0 degree, it will be 45 degree only. So in the transform circuit will look like this. So this is the current value of that transform current source. This is 530 degree ampere that we have already calculated. And with that, this resistance will be this time connected in parallel. So this is the 4 ohm, and they are supposed connected between these two terminals A, B. So this is A and this is B. So they are connected between these two terminals only, they are connected in parallel. And on the other side, this 1045 volt, this voltage source will be now converted into a current source having this value, and that's what is written here, 1.67 angle 45 degree. This is represented in polar form. And this 6 ohm resistor, which was connected in initially is in series with that voltage source, that will be now this time connected in parallel with this current source, and the branch in the middle, that will be connected as it was in the original circuit between these two terminals AB. Now as we can here also we can see that between these two terminals AB, these two current sources are connected, and all these parallel paths are connected, all the where we have this passive element. So we can see that we have only two terminals A and B, and between them every branch is connected in parallel. So the current value of these two current sources, now we can find out that their net value. So here we can see that both the current sources are supplying current in the same direction, and they are in the upward direction. So what we can do is to find out the net value, it will be simply addition of these two values. So it will be 530 degree, and this current source has 1.67 and then 45 degree, and this will be the net current value. But both the current values are given in the polar form. So what we have to do is first we have to convert these values which are given in polar form into their corresponding rectangular form, and then we have to add them. So if we convert this 530, then it will be in rectangular, it will be 4.33, plus J 2.5, and if we convert this 1.67, then it will be 1.1. And now simply we can add them. We have this 4.33 and we have this 1.181. These two real values will be simply added, and the imaginary part of this rectangular representation, they will be simply added, which is J 2.5, and from here it is J 1.181. So these two values, if we add, finally the value that we will be getting is 5.511, and the imaginary part will be, so this much is the value of the net current. And if we want to represent this rectangular format into polar format, then the corresponding polar format will be, or the value will be 6.627, then angle 33.74 degree. How to convert a value which is given in polar format into its equivalent rectangular format, or a value which is given in rectangular, how it can be converted to a polar format, that has already been discussed in the class. Now the transform circuit will look like this, where we have already calculated that value. So the net current value will be 6.627 and angle 33.74 degree and this much ampere. And with that, we have all these three parallel paths. So 6.627, 33.74 degree. And in this circuit, we have this 4 ohm and this 6 ohm. They are connected also in parallel. And with that, this path through which we want to find out the current value, so that is also connected in parallel. So what we do is, so we will simplify these two values, these two parallel paths, 4 ohm and 6 ohm, and we will find out the equivalent resistance. So 4 ohm and 6 ohm, they were connected in parallel. It will be 24 divided by 10, so it will be 2.4 ohm. That's why in this circuit, in place of 4 and 6 which were connected in parallel, in place of that we have this equivalent resistance which has the value 2.4 ohm, and we already had this branch where we had the inductor having inductive reactance value 4j ohm, and for that we wanted to find out the current value. And this is the net, this is the current source, and this is the net value of that current source. Now what we have to do is we have to find out the current value through this inductor. So here we can see every branch is connected in parallel, so here we will apply the current division rule. So if we want to apply the current division rule, and if we want to find out the current value through this inductor, then it will be the, as per the formula, as per the rule, it will be the opposite resistance, which opposite resistance value, which is 2.4, and divided by summation of both the values. So 2.4, and here it is 3 plus j4, so it will be 2.4 divided by, it will be 5.4 plus j4. Now here we can see 2.4 is the value of the resistance, so it can be represented in either way, but in the denominator we have a value which is in rectangular form, but this time we want to divide. So what we have to do is we have to represent both the values in polar form. So it will be 2.4 and then 0 degree, and if we convert this value into polar form, then it will be, so here we have to put the value of the current, which is 6.627 angle 33.74 degree. So now if we multiply these two values, now in the denominator we have values which are given in polar format. So if we multiply them, multiply means this real value, this r and this r will be multiplied, and if we multiply their r value, then it will be 15.91, and their angle values will be added. Since this is 0 degree, so simply it will be 33.74 degree. It can be added easily, divided by, we have 6.72. Since again we want to divide two values which are given in polar format, so simply we will divide this to r value, and the angle value we will subtract from each other. So 15.91, if we divide by 6.72, it will be 2.37, and the angle value is 33.74 degree. From there, if we subtract 36.53, then it will be 2.79 degree. And this is, since this is the current value, so this will be ampere. That means through this inductor, the current which is flowing, that value, so this is the current value, and since this is an AC circuit and we applied AC voltage source, that's why the current which is flowing through this inductor, that is also has the AC value. So it has an magnitude along with the phase angle. So this is the end of this class. Thank you.